Everybody. My name is Brian Kim. I'm currently the VP of Strategy and Operations here. Excited to get this webinar in front of you guys and see what you guys think.
Hi, everyone. I'm Sam Martirosyan. I'm a support engineer here at Superb AI. And likewise, really excited to share what I have with you all.
Cool. Well, Dasha, I'll kind of take the mic from here. Again, everyone, thank you for joining. We know that everyone here must have extremely busy schedules, so definitely appreciate you guys and gals taking the time to join us for this webinar titled Data-Centric Workflows for Computer Vision. We here at Superb AI all think that this is a topic of great interest, not just for those of you in this webinar, but really through our conversations, really just the general computer vision industry. So why this topic? With respect to the concept of data centricity or data-centric AI, there seems to be a general consensus on the principle itself that it's needed. But from our experience, there's not a lot of actual applicable approaches on how to build better data-focused workflows when it comes to building and deploying computer vision applications. So for the purpose of this webinar, our solutions engineer, Sam, as you all met, is going to present some of the concepts around data-centric workflows, how to utilize these concepts to implement more efficient ways to build better computer vision applications, and how to actually use some of the tooling that we provide to harness and implement best practices around this very idea. So without further ado, I'd like to introduce Sam, our very talented solutions engineer who has been hands-on with a lot of our clients in the space. He's had the opportunity to have a lot of conversations with all of our clients around computer vision tasks and really helping them figure out the best ways and approaches to making sure they are building the right data sets for their model. And something very cliche, but it's not about more data, it's about better data. So Sam, take it away.
All right, let's go. So just a little background on me. I studied computer science with a specific focus on computer vision. I've worked as a technical analyst at EggPath, and more recently, I've been working as a support engineer at Datto and a support and solutions engineer here at Superb AI. So let's dive right into the presentation. So today I'm going to be quickly reviewing what is data ops in the context of data-centric operations. Why is data ops crucial for computer vision specifically? What does data ops look like with Superb AI? And then a real-world demo of some of our new data ops modules. All right, so let's start with a quick overview of what data ops is and why it's important. So in short, DevOps is the transformation in the delivery capability of development and software teams, whereas data ops focuses on the transformation of intelligent systems and analytic models by data analysts and data engineers. So at a high level, DevOps is a synergy of development, IT, operations, and engineering teams with the main goal of reducing cost and time spent on the development and release cycle. Data ops is an attempt to apply these insights from DevOps to data. The data teams are going to work with teams of various levels to acquire data, transform, model, and obtain actionable insights. So similar to how DevOps transformed the way in which the software development cycle works, data ops is also changing the primitive practices of handling data by implementing DevOps principles. Another representative of the ops family, ML ops, merges operations with machine learning. It applies DevOps patterns to automate the lifecycle of ML models from their generation to deployment to retraining. Both data ops and ML ops can be viewed as an extension of DevOps methodology in data science. Data ops covers data journeys from extraction to deployment analytics products. It may prepare quality data sets and features for machine learning algorithms, but doesn't offer solutions for training ML models and running them in production. That's where ML ops has the edge. So what brought us to data ops? The 2010s have been widely considered the big data decade. So organizations are generally investing to ensure data teams can continue to scale in productivity, efficiency, and innovation. This is where data ops comes into the picture. So we're dealing with massive volumes of complex data here. This all started with the rise of big data. Basically, any business of any size that you can think of is working with massive volumes of data coming from various sources in different formats. In large organizations, the data landscape is extremely complex. tens of thousands of data sources and formats, including financial transactions, CRM data, online reviews and comments, customer information, and so on. And to answer your business questions, that is to actually make the data useful, the data needs to be in a format that we can understand and use for analysis. So that's why all data that's gathered is going to undergo a series of transformations, data and analytics pipelines. The data is profiled, cleaned, transformed, and stored in a secure location to ensure data quality, integrity, and relevance. Now, for each of these processes mentioned above, you might be using various tools from data cataloging and data profiling tools to analytics and reporting tools, which brings us to technology overload. The people using the tools and technologies to work on your data are also diverse. Data engineers focus on data preparation and transformation. Data scientists worry about getting the right data for their algorithms. Analysts care about building daily or weekly reports and visualizations. IT cares about maintaining data access protocols and guaranteeing data quality, security, integrity. And business managers are keen on finding out whether the business is flourishing. So overall, bringing together these diverse technologies, processes, and people with different mandates creates massive collaboration overhead and possible friction between teams, which is why we need a data ops framework in place. So why is data ops so essential to computer vision? Here's three basic propositions about computer vision model development that we think highlight the importance of data ops. First, in most real-world machine learning projects, including and especially computer vision, the data can be more important than the models. This is in contrast with academic machine learning, which often emphasizes the modeling component rather than rethinking the data paradigm. When trying to improve model performance, it's critical to not only attempt to further fine-tune the model architecture, but to return to the data and see if the root causes of bad performance can be found there. But how do we do this? Managing and preparing unstructured data is fundamentally challenging, particularly when it has not yet been annotated. Data ops tools should be able to help us explore data at scale, visualize the datasets, easily sample and curate subsets, and also assist us in focusing our efforts when collecting and labeling data on the most valuable data points that will bring us the greatest rewards in terms of model performance. And finally, the development of computer vision applications is necessarily iterative, both at the algorithm development level and at the product development level. Data ops principles and tools should support us in continuous improvement and refinement by learning from use case failures, sampling and annotating edge case data points based on these failures, and measuring the new data points against existing data and robustly combining old and new data sets. Let's take a quick look at the data ops pipeline in general before we bring it back to our computer vision applications. So first, we have data acquisition. When we talk about data acquisition, we tend to think about data collection. There are both physical and operational considerations to this, ranging from where to collect the data to how much to collect initially. If we want to get data collection right, we need a feedback loop aligned with the business context. Synthetic data generation is a second approach, with many use cases ranging from facial recognition and life sciences to e-commerce and autonomous driving. However, getting the synthetic data requires a large amount of training data and compute power. And also, synthetic data is often not realistic for distinct use cases, and there's a lack of fundamental research on what impact it might have on model training. And then finally, a third approach is known as data scavenging, which would be scraping the web or using open source data sets like Google Dataset Search, Kaggle, or finding academic benchmarks. And data labeling. Data labeling is an industry of its own because we have to answer some pretty tricky questions. Who should label the data? How should the data be labeled? And which data should be labeled? Indeed, getting the data labeling step right is extremely complicated because it's error-prone, slow, expensive, and often impractical. Efficient labeling operations can require a vetting process, qualified personnel, high-performance tools, its own internal life cycle, a versioning system, and a validation process. And data debugging, the next section of our pipeline, generally entails writing expectation tests to address the data pre-processing and storage systems. So basically, these are unit tests for your data. They're designed to catch data quality issues and bad data before they make their way into the data ops pipeline. Next, we have data augmentation, which is a scientific process where we can manipulate the data via flipping, rotation, translation, color changes, etc. However, scaling data augmentation of bigger data sets, negating memorization, and handling biases and corner cases are still fundamentally tricky issues. Then we have data transformation. This has 3 steps: data formatting, which is a small slice of the whole data engineering task that interfaces with data warehouses, data lakes, and data pipelines; feature engineering, which includes concepts such as feature stores, management of correlations, management of missing records, and going from feature selection to embeddings; and then finally data fusion, which means fusing data from different modalities, sensors, and timelines. And last, we have data curation. This derives from the belief that because our data sets are so large, we need to be intelligently selective about the types of data we're going to use. So we need to catalog and structure the data methodologically. We can sort data by use cases. We can make the data searchable by predefined tags. We can cluster the data via specific embeddings and metadata. This exists within the data ops pipeline, but it also interfaces directly with the MLOps pipeline, as illustrated here. And finally, there's the concept of data selection. In any data sets, there'll be high-value data, which is useful, redundant and irrelevant data, which is useless, and mislabeled, poorly correlated, or low-quality data, which is actively harmful to model development. We, of course, only want to select the useful data samples. All right, so let's take a look at what data ops looks like with Superb AI, what we've identified as specific problems in the data ops space, and what our solutions are to these specific issues. So let's talk about data curation. At a high level, data curation is the process of discovering, examining, and sampling data for a specific analytics or prediction task. In the context of computer vision, data curation is massively underrated, as there are few streamlined methods to understand what kind of data has been collected and to then curate it into a well-balanced and high-quality data set. At a high level, a functional data ops platform for computer vision should have data curation capabilities that enable data and ML engineers to understand the collected data, identify important subsets and edge cases, and curate custom training data sets to put back into their models. More specifically, this platform should be able to visualize massive data sets, discover and retrieve data, curate diverse scenarios, and integrate seamlessly with existing workflows and tools. Training computer vision models requires a constant feed of large and accurately labeled data sets. However, this typically requires a considerable time and capital commitment, especially since most of the time, labeling and quality assurance is done manually by humans. Data labeling and auditing are major bottlenecks within the data preparation pipeline for computer vision systems. An effective data ops platform for computer vision must address these 2 expensive steps of labeling the data and auditing the labels, and needs to support us in measuring and maintaining data quality with testing frameworks. So let's take a look at some of our solutions to these identified pain points. The fundamental pain points for data labeling are speed and quality. Manual labeling is slow, and ensuring label quality can be extremely difficult, specifically for domain-specific data. Our custom auto label module helps you quickly develop a custom model tuned to your exact use case. It can use uncertainty estimation to massively streamline QA of the auto label data, allowing you to focus your QA efforts on hard labels that may be incorrectly auto labeled. We recommend integrating this into an iterative active learning framework to build the custom auto label module's effectiveness as fast as possible, using automation from the beginning and starting only with small initial quantities of labeled data. This can also be used in conjunction with our curation module, further streamlining the active learning process and most effectively allocating your labeling and QA labor. So here are some fundamental pain points we've identified in the data curation process. Without AI, we can query data sets based on metadata or annotations, which limits us to metadata or annotations that already exist, or forces us to allocate labor to generate new metadata or annotations. We can also manually inspect images directly, perhaps selecting interesting images from thumbnails or a tiled view. And this is painstaking and generally not scalable. Random sampling is an industry standard, but has a number of shortcomings. Distribution issues, it can be negatively biased, it can totally miss out on edge cases. To address these pain points, we've developed our data curation data ops module. At a high level, our curation module attempts to improve the distribution of labels between object classes, as opposed to a randomly sampled subset. We also want to empower users to create multiple slices filtered by or prioritizing specific object classes and attributes. More granularly, curation will attempt to generate a more semantically diverse dataset. For each object in the curation superset, it will generate an embedding. It then clusters objects based on these embeddings and their semantic similarity. So within a class of person, it might end up identifying clusters like person at night, person from above, etc. From these clusters, it will pick out edge cases or small sparse clusters and make sure that these are well represented. It will also identify dense clusters with larger numbers of similar images, which are likely to be common or duplicate data types, and will deprioritize these in the final slice. All this information is provided per curation in a report, allowing you to, at a glance, see the distribution of your data, test against a random sampling, and also review a list of the most sparse clusters. Building on this QA and audit functionality further is our mislabel detection module. Manual QA, much like labeling, is necessarily very time-consuming. Our mislabel detection module detects possible incorrect labels automatically by algorithmic comparison with a ground truth set. This module is focused on efficiency improvements in comparison to a random sampling QA by determining labels with a high probability of error, and then showing those labels ranked in order their likelihood to be mislabeled. Let's assume we have 10 incorrect labels out of 100 labels. If we perform a random QA sampling of 20 labels, we'll on average only find 2 of those incorrect labels. Mislabel detection can help make QA efforts more efficient by prioritizing labels that have a higher probability of being incorrect. At a very high level, it can also be used to quickly identify classes that are causing issues without a complete manual QA. Reviewing mislabel detection results can make problem classes immediately visible. This can be used to fine-tune labeling guidelines or as a starting point for augmenting datasets. Further building on these issues that we've identified in relation to both data curation and data auditing is our semantic search module. As mentioned earlier, auditing unstructured data is a really hard problem. We're either limited to searching by metadata or annotations that have already been created, or we're left reviewing images manually. Our semantic search module supports natural language and image queries to gather search results. It does not require the images to be labeled. We can search with uploaded images or use images that are already uploaded to the suite. We can limit queries to specific subsections of images. This has a number of use cases. We can use this to build out edge cases quickly by searching datasets for objects, searching datasets for images that are semantically similar to specific edge cases or objects. In my experience, this has been extremely useful for streamlining label QA. For example, in an initial QA process, we might identify a type of image that appears to be commonly labeled with low accuracy by manual labelers, such as an image with high reflectivity or a nighttime image. And then I can use the semantic search to specifically pull up the images of this sort and focus our QA in on those, which can significantly speed up our auditing process. So while each of these modules can be used entirely independently, DataOps is ultimately about integration and synergy, and we'll see some of the most powerful results by integrating them all into a DataOps pipeline. For example, and as I'll show in the following demo, we can use Curation to select a subset of unlabeled data for initial labeling, ensuring that it's semantically diverse. We can label that data and then train a new custom auto label on this data. use curation again to select our next subset from the remaining data, auto-label this subset, use the difficulty estimation and mislabel detection to speed up the QAing of these new labels, use semantic search also to build out our edge cases and for further QA. And then we can repeat those steps, continually improving the size of our labeled data and the performance of our custom auto label model. And then we can finally use curation at the object level on our labeled data to generate a balanced export from the labeled data and better understand the distribution of the data in our final data set. All right, I'm going to jump right into a demo of our DataOps modules. Okay. So in this demo, we'll be working with a data set of driving images, which is the BDD 100K. Let's say we're trying to label common vehicle classes, people, traffic signs, and lights for a self-driving model or a traffic monitoring system. We'll start with a large number of images here, 100,000. Our first step, as mentioned previously, will be to curate our initial subset for labeling. To maximize the effectiveness of our custom auto label module, we'll want to select both a training subset and an optional validation subset, which is used for internal calibration in the model training. First, we'll create our main training set. As we've mentioned, a critical part of DataOps is the ability to generate intelligent subsets from large unstructured data sets. We could start with a random sample here, but as we've discussed, there are a number of issues with that approach. Let's create an initial 15,000 images. It's as simple as filtering the data set on our label view here to the set that we want to curate from, which in this case is all of our images, so we're okay to go. And then just selecting the curate option. We can pick a name for our curation, call curation training, select the number we're going to curate, which in this case, let's start with 15,000. And we can also optionally select classes. In this case, that's not relevant because we're working with unlabeled data. Okay, so this curation will take a little while to run. This has just been queued. So we'll take a look at a curation that I've run earlier. So this is the same curation of the same size using the same data set. So let's take a look at this result. So we can see a complete list of all the data that's been selected by the curation here. We can select all of this and edit the metadata for the data so that we can export it and use it for labeling. But let's take a look at the curation report created for this data. Okay, so first we see a high-level overview of the number of labels curated and the objects, which in this case is not very interesting because it's all unlabeled data. But let's take a look at the cluster coverage. At a high level, the curation is going to generate embeddings for each of these images and then cluster them based on their semantic similarity. So in this case, the curation has identified a little over 9,000 distinct clusters and has curated so that each cluster is best represented in the sampled data. On the other hand, as you can see, the random set sampling has represented less than half of the clusters in the in comparison. If we go a little further down here, we can dig into the sampling in relation to cluster size. Here we can really start to see the benefits of the curation even more drastically. For clusters of size 1, which is to say images that are sufficiently semantically distinct from all other images in the data set, the random sampling is missing 3/4 of the identified clusters. For clusters of size 2 to 5, it's missing over half. These images could contain critical edge cases, class instances, and as such are more valuable to label than the larger clusters of similar images, where we see that the random sampling is performing similarly to the curation. Scrolling a little further, we can see a quick overview of the semantic space in a two-dimensional visualization to quickly confirm the better coverage of our curation. And then finally, we have a selection of sparse cluster examples and dense cluster examples. So identifying edge cases and maybe image types that are well represented in the dataset. So quickly reviewing this, we can see that our dataset has a number of sparse clusters with images of cars turning at angles to a road, so cars turning into intersections. And it's possible that these are edge cases that may need to be investigated or expanded on further. Looking down at the dense cluster example section, we can see that there's a preponderance of night images. With a large number of similar looking nighttime images, it's possible that these are overrepresented in the data set. All right, let's go back to the curation here. So we can simply just select all images and tag them, and we can tag them training. Okay. And now to generate our validation subset, which is a smaller subset that, as I've mentioned, is used for internal calibration in the testing, we can just filter out all images that have already been tagged and create a new curation, this time of size 2000. Now, in this case, I've already performed and tagged the second curation in advance, just because it's going to take a little while for those to complete. So with this new unlabeled training data set, entirely curated and tagged, the next step is going to be, you guessed it, to label them. So now I'm just going to take a few minutes to label and QA 17,000 images. Just kidding. I'm going to hop over to a different project where this curated subset has already been labeled. So with this data labeled, we can now train a custom auto-label model. First, we'll create an export with the tagged labels in it. So the training and validation subsets. We have 70,000 labels and creating an export, which is what we use for label versioning and extracting label data from the project as well. You can see we can automatically trigger it to create a custom auto label from these labels that are exported. In this case, as the export will take a few minutes to process, we'll take a look at an export that I completed earlier. You can see it's 17,000 labels. And starting training a new custom auto label module on it is as simple as just clicking create custom auto label here. The training for this will also take a little while. So I've already trained a custom auto label on this data. And so setting it up to apply to this project is as simple as clicking apply, confirming that we're going to be using all classes, and hitting apply. Now, with this custom auto label configured, we'll need to select the next training set to work on. As before, we can use Curation to gather a new subset from the training data and label it as test. In this case, I've already run the curation and completed the tagging. Running a configured auto label on a set of labels is as simple as filtering by label, selecting them, and clicking auto label here. In this case, I've also, just for the sake of time, I've already completed the auto label on these 2000 labels. So automation is a critical part of data ops. We've partially automated our labeling process with custom auto label here, and we'll look at some ways to make our QA more intelligent with automation too. The first step in QAing these is probably going to be to use our auto labels difficulty estimation function. We can use the label view here to filter labels by the estimated difficulty. Let's first quickly review some labels that are identified as easy. Okay, as you can see, the auto label difficulty is estimated here, and these are the lowest difficulty. So here are some examples of labels that our model considered easy. As you can see, it successfully identified the vehicles, a person, and the 3 signs. Let's look at another example. We've got several people identified correctly. Looks like all the vehicles have been identified correctly. A truck has been distinguished, and both the road signs have been distinguished. One more, we can see that all the traffic lights have been identified by the custom auto label module, the vehicle, the people, and the truck in the background here. Okay, so let's take a look at, instead of the easy labels, medium or hard labels, which would be the first point of QA for the custom auto label module. So let's pull up this hard label here. As you can see, it's missed some of these more distant cars, and it's missed the traffic lights, possibly because of the blurrier image. Let's pull up another one just for demonstration's sake. Again, we can see a number of vehicles have been labeled correctly, but again, these traffic lights have been missed. So this helps us streamline our QA on images that have a higher probability of being mislabeled. We can also use mislabel detection similarly. One of the big advantages of mislabel detection is that as well as QAing auto-labeled images, it can be used in exactly the same way to QA manual labels as well. So to run a mislabel detection, we will just need to select a query set to apply the mislabel detection to, which in this case will be our test set, and then a reference set, which can be, which in this case is a ground truth subset of labels that we've already validated. In this case, I've already run a mislabel detection on these auto-labeled images, so we can just take a look at it now. So at a high level, it will break down the it will break down the results by class. As I mentioned earlier, mislabel detection has a number of uses. First, we can use it to quickly streamline our QA. I can click through for any specific class to review all possible mislabels in order of their predicted likelihood to be incorrect. And then I can mark them for review by adding specific issues that we can then filter by and have our labelers return to in the suite. So I could add an issue to remove this label that's clearly incorrect. In this case, I could add a label to change the class of this, as it's clearly a traffic light. We can also just scan this list at a very high level. So scrolling down, we can see, let's see. We can see the bicycle class here. It looks like all of these are correct. These are all bicycles. So this would suggest that the bike class may have very few mislabels. We can also see that in general, among these identified mislabels, we have a number of like blurry nighttime images with strong lighting. So if we can quickly identify a high number of certain types of label that have possible mislabels, we may have a class that needs better representation in our model training, or if it's manual labeling, may require better guidelines for our labelers. So another tool that we can use for QA is semantic search. A crucial part of data ops is the ability to efficiently extract individual or multiple pieces of data from massive data sets. This is, of course, even more challenging with unstructured data like images. In this case, we can use our semantic search to investigate types of images that we think have a high probability of being mislabeled to further speed up our QA. As we identified some possible mislabels with blurry lights early on, let's just do a natural language search for blurry lights. And I'm just going to kick off a search here. So with a semantic search, we can use both natural language queries, images, or a combination of both to search the data set. And as I mentioned earlier, this doesn't require pre-existing metadata or annotations. So this is going to take just a minute to complete.
Hey, Sam.
Yeah.
Oh, it's done. I wanted to ask you a question that came in from one of the attendees while we wait, but it's pretty fast. Do you want to take one question?
Yeah, I'll take a question.
So it's a very interesting question. That's why I wanted to bring it up. Amit asked that, for example, for traffic data, let's say you finished one pass of all the steps and realized that accuracy is not high for rain or snow conditions. Can you just add a lot more of those images to your data sets? Or are there any restrictions from the perspective that the data set should be a good representation of actual reality? This question will make more sense if you think of face recognition. So you can have a data set with minority faces amounting to 50% when their percentage in actual population is only 20%. So basically, probably like biasing data set a little bit when trying to make the model more accurate. Do you have any thoughts on that?
That's a great question, I think. And actually, we'll cover it a bit more when we look at the curation of label data at the end of the data set. But absolutely, I think that making sure you have maybe overrepresentation of your edge cases in the data is critical. And so that's sort of what I'm going to look into now, is using tools like semantic search to build out these edge cases more easily from existing unlabeled data. But yeah, I think that makes a lot of sense.
But I think the question here is, will it harm in actuality, meaning skewing the real, world picture of the data set?
Got it. I think that's a really complex question. And that's going to depend on the kind of model training you're doing and the kind of use case you're dealing with. I think certainly in some cases, it's going to be critical to prioritize getting these, sparse edge cases more represented than what might be like a representative data, like data that you've gathered accurately from the world that represents the real world use case. And in some cases, it may be more effective to more closely hew to what the data actually looks like in the real world in the use case. So that's sort of that's a sort of tricky one, I think, and I think is one that's probably going to be resolved best through experimentation and through, again, this data ops pipeline where we're constantly measuring the performance of our model, identifying edge cases and classes that our model performs more poorly on, and then building the data set further.
Awesome. Thank you. That's a great answer. Okay.
Yeah. Yes. So let's pull it back to the semantic search here. So this is just a quick semantic search we ran with a natural language query. And so this is pulled up, as you can see, just a large number of nighttime images with bright lights that are, a number of which are blurry. So we have these like these intense lights that are very blurry, and we can just quickly tag these here, or we can tag them individually and, add metadata here that for further review and use in the suite. So identifying as mentioned, identifying high value labels is going to be like a critical part of data ops. In the mislabel detection, we noticed an issue with a large hanging traffic light that was mislabeled as a sign in our mislabel report. It's possible that our model needs more representation of that class. So let's try a slightly more advanced semantic search. So I'm going to start with a query that I put together earlier. So these are just 4 images that I pulled that have examples of hanging traffic lights in them, I think. And I added these to the query. Let me just go ahead and add another image. I can either upload an image or I can pull an image that already exists in the suite. So I'm just going to search for a key that I know has a traffic light in it. Second. Yeah, this is searching all of the data we have uploaded to the suite. So we can also be a little more precise. By default, the semantic search will use the entire query image for comparison, but we can also select specific regions of the image for our query. So let's select a traffic light from each of these query images. Here we have, I think, the specific blurry traffic light that we had an issue with earlier. Here's another blurry traffic light in the distance. And then we'll kick off the search. So this might take a little longer than the natural language query. This semantic search is something that we can use iteratively. As you see, I started with a search that I'd already ran. We can combine images and natural language queries, a number of natural language queries. It's often quite effective to use a combination of both. And yeah, it's something that you can continue to build on, reusing existing queries, rerunning existing queries to both QA and pull additional data. This should complete in just a minute. Do we have any other questions while I just let the semantic search run?
Yeah. Okay, let me see. What is the biggest image data set that the system can label at one time? Not sure what it means at one time.
So for the
What is
auto,
the max? Oh, okay, sorry, it's the next question. I thought it's never mind. Yeah.
got it. So for auto labeling, it's just a matter of time. The auto label will run pretty quickly, but it's going to take some time for it to label massive data sets. Generally, it'll take less than a second to label an image. This is the auto label model is currently primarily not a production model, but we're looking into this as further productization. But in the immediate sense, this is something that can that can label pretty massive data sets. This is something that I can run on, that I have run in this demo data set on 70,000, 100,000 images. And it's coming back in a relatively timely fashion within, a day or in less than a day or a number of hours. Again, this depends significantly on the complexity of the data and on the number of object classes that are being leveraged.
So there is no maximum that we know of. It just, the difference will be the time it takes.
Yeah, exactly.
And I'm sorry.
Yeah, well, we can come back and touch on some questions in a few minutes, I think.
Okay.
I'll just finish up the semantic search here. So let's take a look at this. So we search specifically these traffic lights. Is loading here. There we go. Okay, and so this is working with unstructured data. So some of these results are not correct because we're working from just a small query image, but already we can see that we've picked out a number of traffic lights that are hanging, that are of the sort that we're looking for here. That are possibly interesting and may continue to improve performance on this specific subset. Again, here. So this is something that we can use. We can select these in bulk, or we can review specific images and use this to build out this specific object class cluster and add them to our next data set for labeling. So as I mentioned earlier, DataOps from its DevOps roots is all about iteration. Each of these modules are designed to be used as part of an iterative workflow, each time improving the quality of our internal auto label model, our labels, and the diversity of our data set. And of course, we do want to export this data for use in external model training. Curation can be used again here, working with labeled data this time to select subsets with a balanced distribution of classes and semantic clusters for optimal model training. So as it was earlier, curation is as simple as selecting the data set we want to work from using our filters here. So in this case, let's just pick them that have existing annotations. So we've got just a little under 19,000 labels, and then we can select a curation here. Let's call it an export curation. Let's just select 10,000 labels. And we can again select the specific classes to prioritize here. In this case, we won't, just so we can get a more general report. But yeah, I'll kick this off now. In this case, I have also run a report earlier. So this one is running now. Here's another curation I ran on all of the labeled data. So let's take a look at the report for this one. This is going to be a little bit more complicated than the curation report for unlabeled images. First, we can see that there are 19,000 images with about 10 objects per image in total. This is the total number of objects. Immediately, we can see that our curation is actually, even though it only includes a little over half the images, has actually included the vast majority of objects in the images. So by prioritizing complex images with high number of objects, it's maximized the number of objects in our export. Similarly, looking class by class, we can see the total count of objects in the data set, and in the data subset, the total count of objects that are showing up in the random sampling, and the total count of objects showing up in the curated sampling. Now, here we can see that the random sampling is, in many of these cases, losing almost half the number of objects. This is especially critical for some of these rarer classes where we're going from 26 instances of train down to 13. We're going from 567 down to 277. And here we can really see that the curation has strongly prioritized preserving every single instance of these rarer classes in the export. So we can also see this graphically represented per class here. So as before, with the unlabeled data, the curation also generates clusters of embeddings. So in this case, instead of doing it for the whole image, it does it one for each labeled object. At a high level, we can see that the cluster coverage of the random sampling is okay for these object classes that are more numerous in the data. So we see out of about a little over 5,000 clusters identified, the random sampling is getting 4,000, 4,000, 3,000. However, we start to see some real issues when we come to the sparse classes with the random sampling, where in fact the random sampling is losing, in these lower cases, more than half of the identified clusters, whereas the curated export is gathering all the clusters. Moving down a little further, we can see this much more starkly on a graphical representation, with the sparse clusters or edge places being severely underrepresented in the random sampling. In this case, we're talking about sparse clusters not on a class level, but across all classes. So again, sparse clusters here, cluster of one being an object that is semantically distinct from all other objects in its class. So the random sampling is missing almost half of these rare edge cases, and it's missing a chunk of these slightly less rare edge cases, or these smaller clusters. The difference between the random sampling and the curation is, as would be expected, gets lower as you have these larger clusters, which are more likely to be picked up by a random sampling. And then the curation also generates these 2D visualizations of the embedding space for each of these objects. We'll just quickly move through these because we're tight on time. But also, interestingly, the curation finally generates an edge case report identifying sparse and dense clusters on a per class level, in the same way that we've seen it identify on a per image level. We can sort of quickly, looking at this here, see that cars that are very blurred, cars that have obscured or obstructed outlines with other objects, or cars that are seen through reflective windows or dirty windows, are semantically distinct from all the other cars in the data set and may require further representation if we want to identify these. So this labeled curation can be used to create a balanced export for efficient model training. As we discussed in answer to the question, it can be sometimes better to overrepresent these sparse or less represented classes in your training data set. But also, it can just be used to gain additional insights about your data set. help you identify the clustering of your classes, identify edge cases, and just help you further understand and improve your data quality. So in summary, I think I've walked through these new data ops modules, how they might work as part of a more general data ops pipeline. I think it's increasingly important to bring a data-centric approach to computer vision development. And we hope that these tools and this more general vision for how they might fit into a broader workflow and data-centric orientation can help do this. And that's it. I think we can take questions.
Thank you, Sam. Yeah, we will maybe spend the last 5 minutes to answer any questions that you guys may have. And again, while you guys are sending those questions over, we will be sending out the recording and a follow-up email. If any of you are interested in trying some of these features out or have any questions about the approaches to data curation, for example, we're more than happy to get on a call with you and just kind of facilitate some Q&A and maybe even some product demos.
While people still thinking if they want to ask some more questions, there was one question earlier. It's pretty general about data ops roles that I don't think we answered, but I think, Sam, you working with our customers and users a lot, you might have some insight. What would be some job titles and their hierarchy falling under data ops? Do you have any idea?
I think that's a really broad question, and maybe Brian will have some more insight on this, but I think that this is in many ways still a very new space. I think we're still working out the organization of how data ops should be handled at an organizational level. So I think that that's kind of a going question. I don't think I have solutions or recommendations. I think we are going to be seeing more data ops and data-centric roles and roles that are focused on data ops and on managing data ops workflow. But yeah, Brian, do you have any thoughts on that?
Yeah, I definitely agree with what you said, Sam. As you mentioned, we haven't seen anybody specific to data ops. It's definitely a much more nascent concept to computer vision and the practitioners involved in building computer vision applications. Typically in a normal engineering organization, you typically find people that actually have the title of data operations or even data engineer that works sort of as the liaison between project and product along with the engineering team to build governance, to build best practices, processes, so on and so forth. So, we definitely want to push this sort of paradigm around data operations and data preparation. We feel that this is probably the best way for us to influence or help sort of push the market in the right direction because we see so many great applications that are trying to be developed in the computer vision industry. And definitely a lot of rules. I want to push that forward, and data operations is definitely something that we advise companies to kind of look into when our clients are trying to expand across their org. So I hope that answered your question.